All right, so please be seated. Okay, so let's continue. So it is our great pleasure to invite Professor Raymond Yeung to give us the keynote speech, Proving Information Inequalities by Gaussian Elimination. So I think almost all of you know Professor Yeung already. So I will also give some introduction to Professor Raymond Yeung. So Professor Raymond Yeung is a Chongming Lee Professor of Information Engineering at COHK. He received BSM Engineering and PhD degrees from Cornell in Electrical Engineering. Before joining COHK, he was a member of technical staff at AT&T Bell Laboratories. He had been serving as co-director of the Institute of Network Coding at COHK. He's the author of the books, A First Course in Information Theory, and Information Theory and Network Coding, which have been adopted by over 100 institutions around the world. In spring 2014, he gave the first MOOC in the world of on information theory that reached over 60,000 students to date. So that's quite a lot. He is a recipient of the 2005 IEEE Information Theory Society Paper Award, the Friedrich Wilhelm Bessel Research Award from the Alexandra Halbert Foundation, and also IEEE Eric E. Summer Award, ACM SIG Mobile Test of Time Paper Award, IEEE Richard Hemming Medal, and also Shannon Award. So he was named Outstanding Overseas Chinese Information Theorist by the China Information Theory Society. He is a fellow of IEEE, Hong Kong Academy of Engineering Sciences, Hong Kong Institute of Engineers, and the US National Academy of Inventors. So let's give our warmest welcome to Professor Yeung to give the talk.
Thank you so much, Lindsay, for the very kind introduction. First of all, I need to apologize to Bai Baoming Laoshi because I gave exactly the same talk at CDN a few months ago, and Chen Chao was not there, so this is new for you. Well, speaking of the MOOC that I produced in 2014, the MOOC has been running on Coursera over and over again, and I truly suspect that it's the same batch of students throughout the years. I don't know. Okay, now the title of my talk today is Proving Information Inequalities by Gaussian Elimination. This joint work with Guolai Gang, who's with Beijing Normal University, and he's also visiting me for the time being, and also Gao Xiaoshan of Chinese Academy of Sciences. Okay, the first part of the talk is a brief review of some existing results, which serves as the background of the research. And the second part is new results. Okay, first of all, for those of you who are not familiar with Shannon's information measures, these are the formulas. I'm sure that everybody here knows what they are. And we also define mutual information, conditional entropy, and conditional mutual information. Okay, back in 1997, actually, well, I mean, more than 25 years ago, I came up with a geometrical framework for entropy inequalities, which works like this. Now, in this talk, an information inequality refers to an inequality that involves only Shannon's information measures. For example, this one, which happens to be a valid one. And now, the one observation to start with is that all Shannon's information measures are linear combinations of entropies. Okay, so these are displayed in these formulas here. And because of this, we only need to consider inequalities of joint entropies instead of considering all the four types of Shannon's information measures. Okay, and in short, we call them entropy inequalities. Okay, so in this framework, we first fixed the number of random variables to be n as a definite number. And for n random variables, x1 up to xn, there are 2 to the power n minus 1 joint entropies. For example, when n is equal to 3, there are 2 to the power 3 minus 1 equals 7 joint entropies, namely the entropy of the individual random variables, entropy of the pairs, and entropy of all the 3 random variables. Now, for each collection of n random variables, we can compute the associated 2 to the power n minus 1 joint entropies. Now, by regarding, we think of this as a vector in this 2 to the power n minus 1 dimensional Euclidean space. By regarding the coordinates being corresponding to the joint entropy of the subset of random variables. Okay, so this is an illustration. Here I try to represent a high-dimensional Euclidean space in 2 dimensions with the axis labeled by the entropy of some subsets of random variables. Okay, so as I mentioned, now for a collection of n random variables, or you can think of it as the joint distribution for n random variables, you can compute the 2 to the power n minus 1 joint entropies. So this becomes a vector in this Euclidean space, and we plot a point there. Okay, and then we can do this for every collection of n random variables, and we keep doing this. Okay, and we just for each collection of n random variables, we plot a point there, and then we take the union of all these points to form a region which is denoted by gamma n star. Okay, now star means something important in this context. So this is the region in the Euclidean space such that H is an entropy vector, means that it's the entropy vector of some joint distributions. Okay. Okay, now it turns out that for this region gamma n star, if you take the closure, it is a convex cone. That's why I represent it in this fashion. And as we're going to see, gamma n star actually is a very important region because it characterizes all entropy inequalities involving n random variables. Okay, so let's take a look at the first case. We want to see whether an inequality B transpose H is greater than or equal to 0. B transpose H is nothing but a linear combination of the joint entropies. So this is gamma n star, and in this situation we have B transpose H greater than or equal to 0, whose half space completely contains the region gamma n star. Okay. In this case, we say that we can see immediately that B transpose H greater than or equal to 0 always holds, because for any entropy, if you have any n random variables from joint distribution, you can compute the entropy vector, and the entropy vector must be a point inside this region gamma n star, which is completely contained in the half space. Therefore, the inequality B transpose H greater than or equal to 0 is satisfied. Okay. So in this sense, we say that B transpose H greater than or equal to 0 always holds, which means that it holds for all joint distribution. Okay. So this is the geometrical meaning of an entropy vector that always holds. Okay, the other situation is like this. So again, we have gamma n star like this. But in this case, B transpose H greater than or equal to 0 has the half space cutting through the region gamma n star. And in this case, we can come up with a joint distribution for the n random variables whose entropy vector lies on the wrong side of the inequality. Okay. In this case, we say that the inequality does not always hold. Okay. Okay. Now, there's another region denoted by gamma n, which is closely related to this region gamma n star. So this is the region defined by the so-called basic inequalities. So we all know that the following inequalities, namely that all Shannon's information measures are non-negative, holds for all joint distribution. Okay? So we call them the basic inequalities. And now each basic inequality is actually an entropy inequality because the left-hand side, this is the left-hand side for you, okay? Because the left-hand side can be expressed as a linear combination of joint entropies, okay? So so each of these inequality corresponds to a half space that cuts through the origin, and then we take the intersection of all these half spaces to form the region gamma n. And because the basic inequalities are satisfied by all joint distributions, we know immediately that gamma n star is a subset of gamma n. Okay, so gamma n star, which we're very familiar with, is actually is an outer bound on gamma n star. So for this purpose, we are going to talk about a special form of Shannon's information measures called elemental forms, for a reason which will become clear. Now, it turns out that if you fix n, the number of random variables, all Shannon's information measures can be expressed as a sum of not a linear combination, okay, as a sum of the following two elemental forms. The first form is the entropy of xi given the rest of the random variables, I not equal to j not equal to I. The second form is the mutual information between xi and xj, where I is different from j, given the sum of the rest of the random variables. So for example, let's say we fix n equals 3. Note that to talk about the elemental form, we need to first fix the value of n. Otherwise, no, it's not well defined. Now, first of all, for the first line here, entropy of x1 given x3 is equal to entropy of x1 given x2 and x3, plus the mutual information between x1 and x2 given x3. Okay? We all know that is true. Now, the first term corresponds to the first type of elemental form. The second term corresponds to the second type of elemental form. So please pay attention to the color code. Okay? The red corresponds to the red, and the blue corresponds to the blue. Okay. Now, the second inequality is just the chain rule. So I x1 semicolon x2 x3 is equal to I x1 x2 plus I x1 x3 given x2, and both of these are of the second form. Okay, so this is the mutual information between two random variables given sum of the rest. Okay, in the first case, you're given nothing, right? Oops, okay. So with this, we can define something called elemental inequalities. So every elemental form of Shannon's information measures is non-negative because they are a form of Shannon's information measures. Okay. So accordingly, we have two forms of elemental inequalities: the first type and the second type. Okay. Okay. The total number of such inequalities is equal to this, which unfortunately grows exponentially with n, the number of random variables. Okay, this actually causes much problem in terms of computation, as we are going to see. Anyway, so this is the important thing to note is that the elemental inequalities are actually equivalent to the basic inequalities, although they are a subset of the basic inequalities. The reason is the following. Now, evidently, the basic inequalities implies the elemental inequalities because the elemental inequalities is just a subset of the basic inequalities. On the other hand, I claim that the elemental inequalities also imply the basic inequalities. A quick example. So previously we have seen that this quantity, entropy of x1 given x3, is equal to the sum of this and this, right? So if you, we know that both of them are non-negative. If you add up this inequality, you get this. Okay. So by adding up some of the elemental inequalities, you can recover all the basic inequalities, and that's what the idea is. And so it's not difficult to see that the two sets of inequalities are equivalent. Although, you know, from the computational point of view, we prefer to work with the smaller set, which is the elemental inequalities. Okay, so with this, we can redefine the region gamma n. And previously, we defined gamma n to be the intersection of all the basic inequalities, but now we can define it to be the intersection of all the elemental inequalities. And we denote this as gamma n equals h in the Euclidean space, such that g h is greater than or equal to 0. But this g captures, you know, this matrix that captures all the coefficients of all the elemental inequalities. Okay, so next with gamma n, I'm going to introduce something called the Shannon type inequalities. Okay, so this is gamma n star, and gamma n we know is an outer bound on the gamma n star. And suppose we have an inequality that whose half space completely contains the region gamma n. Okay, in that case, then we call B transpose H greater than or equal to 0 a Shannon type inequality. Now, I mean, geometrically it means that it is, although it needs a proof, but intuitively it means that it is everything that can be implied by the basic inequality. Okay. Now, the important thing to note is that a Shannon type inequality it holds for all joint distribution. Why is that? Because for any joint distribution, you compute the entropy vector. It is a point containing gamma n star, which is contained in gamma n, and gamma n is contained in this half space. So it lies in the right side of the inequality. Okay. Now, in 1998, with the help of my close collaborator, Yeung, we discovered the first non-Shannon type inequality for 4 random variables. Okay, it turns out that for 3 random variables, there exists no such inequality. So what exactly is a non-Shannon type inequality? Now, previously, I said that the gamma 4, okay, is an outer bound of gamma 4 star, but it's not clear at that point. Was not clear to us that gamma 4 is a tight outer bound on gamma 4 star. Okay, and it turns out to be the case when n is equal to 3, but for n is equal to 4, it turns out not to be the case. Specifically, this non-Shannon type inequality that we discovered, usually is referred to as a Z198 in the literature, and because there was another conditional non-Shannon type inequality, Z197, that we discovered. So we need to make a distinction. And sometimes on the literature, it's also referred to as the Zhang-Yang inequality, which is referred to Z198 instead of Z197. So for Z198, now what it does is that it actually cuts through the gap between gamma 4 star and gamma 4. Okay, so there's a real gap between gamma 4 and gamma 4 star, meaning that even if you take the closure of gamma 4 star, it is strictly smaller than gamma 4. Okay, so this came actually quite at a surprise, because for a very long time we used to think that we are playing around with all these non-Shannon type. I'm playing around with the Shannon type inequalities. Okay, but it was not clear whether. I mean the problem was not well formulated during that time, I would say. So that the problem was not well formulated to the point that we could ask whether there exists any inequalities beyond Shannon type inequalities. But once with this geometric framework formulated, then I think it's not, one would ask whether two regions are the same or not. And that's how the whole story came about. Okay, so the gamma 4 star, as I mentioned, even if you take the closure, is not equal to gamma 4. And I would like to point out that Zheng actually made a main contribution to the discovery of this inequality. I really owe him a lot for that. I would say that without his involvement in this work, very likely even today, we won't know whether there exists any non-Shannon type inequality or not. I'm going to explain to you why. Okay, so subsequently, other non-Shannon type inequalities were discovered by Doty, Freiling, and Ziegler, who use some software tools that we developed back in the mid-1990s together with a technique discovered by Zheng, and also with the help of a supercomputer, they were able to discover a number of non-Shannon type inequalities. And Matouche in 2007 proved analytically that for 4 random variables, there exists an infinite number of non-Shannon type inequalities. So if you're interested in this topic, then I would recommend you to take a look at Terence Tao's blog entitled Special Cases of Shannon Entropy. Okay, now it turns out that this region gamma n is closely related to other fields in some unexpected ways. Now, on the right-hand side, we have a network coding, Kolmogorov complexity, a special combinatorial structure, and finite group theory. Okay, it's a two-sided correspondence. That's why we have arrows pointing to both directions. So and then this region gamma star, or the study of entropy inequalities, also have implications in probability in terms of condition independence, quantum mechanics, cryptography, matrix theory, and matroid theory. In this talk, in the interest of time, I won't be able to go through all of these, but I would like to give you a taste of what this correspondence could be. So this is a joint work by my former student, Terence Chen, back in 1999. He was my master's student then. So so we let G be a finite group and G1 up to Gn be subgroups. So it's any finite group G and any subgroups G1 up to Gn. And we use this notation G sub alpha to denote the intersection of Gi, I in alpha. Okay. So which turns out also to be a subgroup. Well, there's a one-to-one. It turns out that there's a one-to-one correspondence between entropy inequalities and group inequalities in the following way. As an example, we know that this holds for entropy for all random variables x1, x2. Okay. Now, here I'm going to construct a corresponding inequalities for finite groups. So for h, you write log, and then there's a fraction here. Upstairs we have the order of g, and downstairs, okay, this x1 we write order of g1. Okay. Same thing, we transform this term into this term. And on the right-hand side here, h again becomes log, and upstairs we always have order of g. And here in the entropy domain, we have x1, x2, and correspondingly we write a g1 intersect g2, and then we take the order. Okay. It turns out that if the inequality for entropy holds for all joint distribution, which is the case, then the inequality on down there for the finite group also holds for all finite group G and finite subgroups G1 and subgroups G and G2. And this correspondence not only is one way, but it's both ways. Okay, if you somehow discover such an inequality in the finite group domain, then you can also infer that's the same the corresponding inequality holds for entropy. Okay. So this is a rather peculiar correspondence, and if you start with a non-Shannon type inequality, right, Then by going through this, you would obtain what I refer to as a non-Shannon type group inequalities. Okay, so that through this we can generate many new inequalities, and it's not clear what they mean at this point. Okay? One thing I would like to point out is that for such non-Shannon type group inequalities, up to now there's no direct group theoretic proof. Okay? We need to go through entropy and then through this transformation to prove that this is true. I think it would be a very interesting result if some of you can find a direct proof for such a group inequality. I think that would shed a lot of light on its group theoretic meaning. Okay, now next I'm going to put this aside and talk about the computational side of the problem. So in information theory, we very often impose constraints on the joint entropies. For example, for mutual independence of three random variables, we can express this as entropy of x1, x2, x3 equals the sum of the entropy of the three random variables. And for Markov chain x1, x2, x3, and x4, we can express them as these two equalities. The first one is I x1, x3 given x2 is equal to 0, which means that given x2, x1, and x3 are independent. And the second equality says that given x3, the pair x1, x2, and the random variable x4 are independent of each other. Okay. So these two actually specifies the Markov chain. Okay. So it's very common for us to impose constraints on the joint entropies. Okay, now so how do we verify Shannon type inequalities? Now this is something actually quite important toward the discovery of non-Shannon type inequalities, because if you propose an inequality to be of non-Shannon type, you have to first verify that it is not a Shannon type. Okay, so you have to find a way to verify a Shannon type inequalities before you can talk about non-Shannon type inequalities. So we came up with a software package called ITIP. It was back in 1996. I did this together with my final year project student, Yeung during that time. Okay, so the idea is like this. So suppose we have a constraint QH equals 0, and we want to check whether B transpose H greater than or equal to 0 is a Shannon type inequality or not. Okay, it turns out that you can view this as an LP, namely that you want to minimize B transpose H as the objective function subject to QH equals 0. These are the linear constraints you impose on the entropies, and GH greater than or equal to 0. These are all the elemental inequalities. Okay. And if for this LP the minimum occurs as 0, then it verifies that the B transpose H is a Shannon type inequality. So geometrically, this is very clear. So the idea is like this. Okay? So this is gamma n, and this we want to check whether B transpose H greater than or equal to 0 is a Shannon type inequality. So this is this line represents B transpose H equals C, and we want to minimize C. Okay, so if it happens that the minimum occurs at the origin, then we can see geometrically that the half space B transpose H greater than or equal to 0 completely contains gamma n. Okay. Although it needs a proof, but I mean geometrically it is completely convincing. Okay. Whereas on the other hand, if the minimum does not occur at the origin, then it would be a situation like this. Okay, this B transpose H greater than or equal to 0. In that case, the minimum will occur at minus infinity. Okay. Okay, so the only thing is that we want to check, going back to this. Okay, the only thing we need to check is whether the minimum of this LP is equal to occurs at origin. So it becomes a computational problem to verify whether an inequality is of Shannon type. It is a computational problem. Okay, so throughout the years, there have been a number of variations of ITIP. So we first put together this on MATLAB. And then there was XITIP by DeGarvi and his group at EPFL then. It was on C. And then AITIP, I was joint work by myself with Siwei Ho, Ling, and also Chiwei Tan. Okay. So this is actually a web-based thing. And then the mean ITIP actually should be produced by Chemas. And OXITIP is a web version of XITIP. And Chao Tan, Chao Tan had created a computer-aided investigation tool, which I'm going to talk about a little later. And then we have PSITIP produced by my colleague Chuck-Ting Lee. It's a Python-based software package. And then during the last 2 years, with Lai Gang and Gao Xiaoshan, we introduced an LP reduction method for verifying Shannon type inequalities, or actually related types of inequalities. So these are the works published in the IT Transactions last year, and we also have some new results presented at AICIT this year. And among these, those I color code. Those I color code are available on the internet, so you don't have to install anything on your computer, and you can give it a try. Okay, for those of you who are interested on this topic, I will refer you to this expository paper by myself and my colleague Chuck-Ting Lee that appears in the first issue of IEEE Bits. Okay, so I'd like to mention some applications of the ITIP approach. First of all, to me, ITIP is like a calculator for information theorists. If you come up with something, you want to give it a try, the first thing to do is to check it out whether it can be provable on ITIP. Now, it is also, as I mentioned, instrumental in discovering new non-Shannon type inequalities. I mentioned that if you propose a non-Shannon type inequality, you first have to verify that it is not a Shannon type inequality. And beyond that, as I mentioned, Doherty, Frieding, and Ziegler, use with the help of a supercomputer, were able to discover some non-Shannon type inequalities. But they did it with a version of ITIP and also a technique called a copy lemma invented by Jun Zhang. Without this copy lemma, even a supercomputer cannot discover a non-Shannon type inequality. And not only that, after more than 25 years, the copy lemma continues to be the only tool that can possibly identify and discover and prove non-Shannon type inequalities. Okay? We know no other way that can do the job. Okay? That's why without Jun Zhang, involved in this problem, we are probably still in vain in the search of non-Shannon type inequalities. And about 10 years ago, Chao Tan also used an ITIP approach to establish the rate region of a 344 exact repair regenerating codes. Okay, so before I move on, I would like to mention an alternative approach to verifying a Shannon type inequality. Previously, I talked about solving an LP for the verification of a Shannon type inequality, but you can as well use this alternative approach. This theorem says that B transpose H greater than or equal to 0 is a Shannon type inequality if and only if it is a conic combination of the elemental inequalities. A conic combination means a linear combination with non-negative coefficients. Okay. Now, if an inequality is a conic combination of the elementary inequalities, then obviously the Shannon type, right? But you have to prove it the other way, and it is a consequence of the duality theorem of linear programming. Okay. So, well, this is actually quite intuitive, although you need to prove, but the concept is quite intuitive. Now, here are the recent results. Okay, now I mentioned that there are a huge number of elementary inequalities. There are even more number of basic inequalities, but even the number of elementary inequalities already grows exponentially with n. So for the ITIP approach, we need to solve a very large LP. We have this number of variables, okay, because n random variables correspond to the power n minus 1 joint entropies. And we have this number of elementary inequalities, right? Both are difficult to handle. And so in practice, it's actually usually quite difficult to solve, to handle more than 20 random variables, even with today's computing power. Now, this good news and bad news. The bad news is that the elementary inequalities are non-redundant, meaning that you need every one of them when there's no constraint. Right? When there's no constraint on the entropy vector, then there's nothing you can do. Okay? You cannot simplify the problem. However, if you impose constraints on the entropies, some of these inequalities can become redundant, right? Which is the good news, because in most information theory problems, we impose usually a lot of constraints on the entropies, and that can give us some hope to simplify the problem. Okay. Okay, here's a problem formulation. So we let our hx be the set of all homogeneous linear polynomials in X with real coefficients. So this small h here in the subscript denotes homogeneity. Right? Homogeneous means that there's no constant term. Okay? So in this talk, all inequalities are assumed to be homogeneous, which happens to be the case. Like all these basic inequalities, elementary inequalities, there's no constant term in the inequality. Okay, so all inequalities are assumed to be homogeneous, namely it has the form f greater than or equal to 0, and where f is in Rh of x. Okay. And similarly, all equalities are assumed to be homogeneous. Again, this is the case. Consider the independence of random variables or Markov conditions. For all these constraints, there's again no constant term are involved in the constraints. So here's the problem. The objective inequality is f greater than or equal to 0. The constraints are the elemental inequalities, and we can have additional constraints, equality constraints, CE equals 0. We may also impose some additional inequality constraints. For example, you can, for more than four random variables or more, you can throw in some non-Shannon type inequalities that you know, okay? So this can also be part of the constraints. And so this is the setup of the problem that we need to solve. Okay, so again, please pay attention to the color code here. The red denotes inequality, okay? Blue is equality, and green is the objective inequality. Everything is homogeneous. Okay, so the related works, as I mentioned, are the works last year and the work this year. So the objective is to develop an approach that can significantly reduce the size of the LP. Okay, so this was the main goals in the paper last year. And then this year we built on this work to further reduce the computational complexity. And in some cases, as you're going to see, there's no need to solve an LP. Only you only need to apply Gaussian elimination in the right way, and then you'll be able to solve the problem completely. Okay, so the idea is to reduce the problem to a bare bone by exploiting the algebraic structure of the problem. So we have devised a procedure based on 5 building blocks. Algorithm 1 is for dimension reduction, algorithm 2 for LP reduction, algorithm 3 for pre-processing the constraints, algorithm 4 for heuristic search for a conic combination. By the way, conic combination means a linear combination whose coefficients are non-negative. Okay. In case you're not familiar with this terminology. Algorithm 5 is to solve the final problem. Actually, we run these algorithms, and it may some of these algorithms may already produce the results. You don't have to run it all the way to algorithm 5. Okay, I'm going to give a brief description of each of these algorithms. The first one is for dimension reduction. So the setup is like this. We let S be an inequality set and E be an equality set. So we reduce S by E by, again, S means inequality, and I mean red means inequality and blue means equality. So we reduce S by E by the Gauss-Jordan elimination, okay, to obtain the remaining set R. So then with this, the dimension of the problem is reduced. So a quick example. So we have S greater than or equal to 0 being this set of inequalities, and E equals 0 being this set of equalities. So first we apply Gauss-Jordan to obtain this, okay. So this, we denote this by E tilde equals 0. And this is called a reduced row echelon form, or RREF. Okay. And here x1 and x3 are the pivot variables, and x2 is the free variable. And then we substitute the pivot variables into S greater than or equal to 0. And finally, we obtain x2 greater than or equal to 0. This is what we call denote as R greater than or equal to 0. And where x2 is the only thing left are the free variables. Okay. Now, before I talk about algorithm 2, I would like to introduce some auxiliary variables, which is the main idea of algorithm 2. Okay, the observation is the following. Suppose we have a constraint fx greater than or equal to 0. We can replace this by one equality and one inequality, okay, by introducing an auxiliary variable x. So we write fx minus a equals 0, okay, or fx is equal to a, and a greater than or equal to 0. So it's obvious that these two gives the same constraints on x. Okay. So the idea is like this. Now, okay, for each of these equality constraint, we introduce an auxiliary variable. Okay, so we put minus a1 here, minus a2, minus a3 here, and then we apply Gauss-Jordan to this to obtain this. Then we call this the first. Okay, the left-hand side consists of 3 rows, and for the first 2 rows, we call this a partial reduced row echelon form, and we call this J0 of x comma a. The reason is that for these 2 rows, the x's and the a's are involved. Whereas for the 3rd row, we call this give a different name to. We also call this a partial REF. We give it a different name. It's J1 of A because only a's are involved. Okay. So these are called the partial reduced row echelon forms. Okay. So the for algorithm 2, which is the LP reduction, the input problem is to prove f0 of x greater than or equal to 0 subject to some Fix greater than or equal to 0. Okay. So we for all I, we let GI equals Fi minus AI, where AI is greater than or equal to 0. So by introducing this auxiliary variables, we actually don't change the constraints. And then we apply Gauss-Jordan to GI, okay, this collection of GIs, okay, to obtain the partial row epsilon, partial row reduced row echelon forms J0 x of A and J1 of A. And then we reduce the objective inequality F0 of x by J0 x comma A, okay, to obtain F x comma A. Okay. So we use this partial REF to reduce this. Okay. Now the input problem is now reduced to F0 becomes F of x comma A greater than or equal to 0, subject to J1A. We already have substituted J0 x comma A, so we don't need that anymore. And also the constraint AI greater than or equal to 0. So this is the constraint we impose on the auxiliary variables. Now we look at with this form of the objective inequality Fx comma A, if it depends on x, then the problem is not solvable. We can tell this immediately. I'm going to explain to you why. Okay? It's a very simple observation. So if you run algorithm 2 and it turns out that F the left-hand side depends on both x and a, then you know that you're done. The problem is not solvable. Okay, why is that? Now, suppose we want to prove x1 plus x3 greater than or equal to 0 subject to x1 and x2 greater than or equal to 0. Okay, so you run algorithm 2, it would output prove x3 plus a1 greater than or equal to 0 subject to a1 greater than or equal to 0. Now, obviously it is not solvable because the constraints only involve a1, but the objective function has x3 in it. Okay, so let's say a1 is some positive values, and you can always make x3 very negative to violate this inequality. Okay, so that tells you immediately that the problem is not solvable. So therefore, from for the rest of the talk, we will assume that the output of algorithm A2 F depends only on A. Otherwise, we know that we're finished. Okay, there's another notion. There are two other notions that I would like to introduce. One is called the implied equality, and the other one is called redundant inequalities. Now, consider the constraints. Okay, F1, Fia is equal to 0 and Aj greater than or equal to 0. Okay. Now, Ak equals 0 is an implied equality if Fia equals 0, this collection, and the collection Aj greater than or equal to 0 implies Ak is less than or equal to 0. Because Ak greater than or equal to 0 is one of these inequalities. If these together imply Ak less than or equal to 0, it means that Ak must be equal to 0. Okay, we call this an implied equality. Another notion is called redundant inequality. That's more straightforward. If this set of equalities plus these set of inequalities Aj greater than or equal to 0, J not equal to K, implies Ak greater than or equal to 0. It means that you don't need Ak greater than or equal to 0 because it is implied by the rest of the constraints. Now, the usually implied equalities and redundant inequalities are not very readily recognizable. Okay. However, there are some trivial situations that you can recognize them easily, and that's why we call them trivially implied equalities and redundant inequalities. So consider the same set of constraints. Now, in some cases, such things can readily be identified. So let's say we consider FIA equals summation PJ AKJ, summing over some J, summing over J over some sets. Okay. Now, the PJs are non-zero. Okay, for those zero terms, we just don't show them in the summation. Now, if PJs all have the same sign, then for all AKJ, for all J, AKJ equals 0 are trivially implied equalities. Okay, so what it means is that in this summation, if you find that all the PJs have the same sign, whether they're all positive or they're not all negative, then all these things must be equal to 0. I'm going to give you a quick example in a moment. Now, another situation is that if PJ star is a unique coefficient that has a different sign, meaning that among all these coefficients PJ, if one of them has a different sign from the rest, okay, meaning that one is negative and the rest are not positive, or one is positive or the rest are negative, then if the J star 1 is the outlier, then the AKJ star greater than or equal to 0 is a trivially redundant inequality. Okay. So these are actually quite straightforward by seeing some examples. Okay, so suppose we consider the constraints FIA equals 0 for I equals 1, 2, and AJ greater than or equal to 0, where F1 is equal to this and F2 is equal to this. Okay. Now, here, in F1, both coefficients are -1, so they have the same sign. Okay. Then I claim that A1 equals 0 and A2 0 are trivially implied. The reason is the following. So F1 is equal to minus A1 minus A2 is equal to 0. Okay. If you take the negative of that, becomes A1 plus A2 equals 0. Okay. Just both A1 and A2 I'm sorry, let's say A1 yes, okay. Okay, so if you have let's see. Okay, yes. A1 plus A2 is equal to 0, and A1 and A2 are both non-negative. Then immediately you must have A1 and A2 all equal to 0. Okay. And that's why we have these two being trivially implied equalities. Okay. So in this case, you can easily recognize the situation. And the other case is that A4 greater than or equal to 0 is trivially redundant inequality, because now we have F2 equals A4 minus A5 minus A6 equals 0, meaning that A4 is equal to A5 plus A6. Okay? And we know that A5 and A6 are non-negative, and therefore A4 must also be non-negative. So it's just like that. Okay? All right, so so the purpose of algorithm 3 is to pre-process the constraints. So we are given these constraints, and algorithm 3 simply removes all the trivially implied equalities and trivially redundant inequalities. Okay. Now, we have further developed algorithms that can remove all implied equalities and all redundant inequalities, but this would require more computation. So that's a trade-off. Okay? If you spend more time to simplify the problem, then the problem will become easier to solve, but then you already have spent more time simplifying the problem. Okay? Okay, so the next I would like to talk about a consequence of Kappa-Gauss lemma, which is a generalization of the result that I obtained in 1997 in the context of entropy, but there's nothing to do with entropy. So the result says that we have these homogeneous polynomials x1 up to xk and h, okay? H1 greater than or equal to 0 up to hk greater than or equal to 0 implies h greater than or equal to 0, if and only if h is a conic combination of h1 up to hk. Okay, so this is also, you know, convincing. Okay. Now with this, we can devise a heuristic search for a conic combination. So we want to prove F1 A greater than or equal to 0 subject to this set of equalities and this set of inequalities. Now, if F1 of A contains all positive coefficient, okay, these are the A's, right? All the AJs are non-negative. If all the coefficients here are positive, then you know you're done, right? However, if F1A contains a negative coefficient, then we try to use these equalities to eliminate the negative coefficients with the hope to eliminate all the negative coefficients. Okay, if successful, then the problem is solved. If not successful, then you at least reduce the problem to an even smaller one with that contains no implied equality and no redundant inequalities. Okay, so if you're successful, you end up having this, which is a smaller LP. Now here's an example of algorithm 4. So we have this greater than or equal to 0. We're going to prove this subject to AI greater than or equal to 0. So here we have a negative coefficient. Okay. We are subject to this and together with these two equalities. Okay. So there's a negative coefficient here, so we have to deal with it. And the first thing to do is to use this equality to substitute A2 into this inequality to obtain A1 minus 3A3 plus 2 times A4 plus 3 times A5. So again, you have a negative coefficient. Okay, so we don't know the problem can be solved or not. So we use the second step is to use this equality constraint to eliminate A3. So we substitute A3 into here, and finally we get A1 plus 5 times A4. So we are lucky. We end up having all the coefficients being non-negative. Okay, so this shows that this actually is true. Okay. So now one remark is that algorithm 4 is just a heuristic. It may not be successful even though the problem is solvable, but it at least reduced the size of the problem. So finally, we solve the final problem. We want to prove this subject to this and this. And in the interest of time, I just want to say that this can be determined by solving an LP for discriminating conic combinations. Okay, I won't get into the details. I just want to, so at the end, the algorithm with outputs either solvable or unsolvable. Okay, so I'll skip this. So the problem is like this, okay? So we have an objective inequality. We have the constraints, which are the elemental inequalities, additional constraints, and additional equality constraints, and okay. And also some additional inequality constraints. So what we do is that we use algorithm to reduce this. Okay, E and C are the same thing. Okay, and then in the interest of time, maybe I'll just say that you run through algorithms 2 to 5, and then at the end you would be able to tell whether the problem is solvable or not. Now, so let me just give you an example to show you how well it behaves. So I mentioned the in 2004, I forgot it's 13 or 14. Okay, Child 10 disprove a conjecture on the rate region for the 433 exact repair regenerating codes. And with this, he needs to establish an entropy inequality. Okay, the problem involves more than 4,000 variables. Okay, so we solve the problem using a direct LP method. It involves more than 4,000 variables, more than 22,000 equality constraints, and more than 67,000 inequality constraints. Okay, with ITIP, you do the dimension reduction. You reduce the number of variables to 600. No more equality constraints, but you still have the same number of inequality constraints. Okay, now Child 10 has a very clever way. He observed that the problem for regenerating codes is highly symmetrical. So he had a very clever ways to take advantage of the symmetry of the problem, and he was able to reduce the number of variables kind of like manually, right, to 176, and the number of inequality constraints to slightly more than 6,000. Right. Now, with our work last year, without knowing the structure of the problem, without even taking explicit advantage of the symmetry of the problem, we only take advantage of the algebraic structure of the problem. We managed to reduce the number of variables to 101, and the number of inequality constraints to 600 something. Okay. Now, with our latest work, we are just lucky. Okay? We run through algorithm 1 to 5, and it turns out that we don't even need to solve an LP. Right? So this is the at least a performance proof of the algorithms that we have developed. So I just want to mention that our algorithms are developed using symbolic computation, so you can get closed form solutions, and also you can produce human readable proofs. So for further details, I would refer you to these two works of us. Okay, thank you very much. Sorry, I overrun a little bit.
So, thanks, Professor Yeung's talk. So, any questions from our audience?
Yes.
We present the elemental form of the Shannon convention. But there are two forms: the conditional entropy and the conditional mutual information.
Exactly.
As we all know, the mutual information can be decomposed as the discrepancy between entropy and conditional entropy.
Right.
What is the necessity of having the mutual information staying as an elemental form?
Actually, I'm not exactly sure what you mean, but what you said seems to be able to go beyond the domain of entropy, right? I think.
Because by my understanding, the mutual information can always be represented as entropies.
Yes, as a linear combination of the entropies. Yes.
Discrepancy between, let's say, entropy and conditional entropy. But in your presentation, you show the mutual information still stays in as an elemental form. So it means that in this case, the mutual information could not be further decomposed into conditional entropy. So what's the optical in behind?
Is everybody please say the last statement again?
You imply that the mutual information cannot be further decomposed as a linear combination of entropies.
No,
That is the elemental.
No, it's not that. The elemental form is the main thing about the elemental form is that the elemental form is just some special form of Shannon's information measures. Okay, the main idea about the main thing is that is here. Okay, any Shannon's information measures can be decomposed into the sum of elemental forms. That's the main thing, and that's why it has nothing to do with whether these can be further expressed as linear combinations of entropy or not. Nothing to do with that. With this, the set of basic inequalities can be reduced to the set of elemental inequalities. That's the only thing. That's the only use of considering a small set of Shannon's information measures.
So in this case, for example, the mutual information can be
Yeah. You just write this as on the left hand side as entropies, but you reduce the number of inequalities. Because some of for example the basic inequalities on the right hand side is implied by the two elementary inequalities on the left hand side. Yeah. Yes.
I speak Chinese.
Of course.
因为这个我看你的伽马 A 的定义啊，伽马 A 困惑这个，伽马 A 的定义，它是说你给 n 个 x 变量，然后呢，我们可以计算很多这个商，有2的 n 次方减1个商，
没错。
然后计算出来这些商呢，就构成时空间的一个点。
对。
然后呢是便利了所有的分布，把这个点便利了怎么样的？
你考虑所有的分布，然后它就形成一个区。
对，也就是说，实际上我只有 n 个变量，一般应该来讲，我们都谈的离散的，对吧？离散变量。那么我们有了这个 n 个离散的变量，然后这个 n 个离散的变量上面呢，它的分布呢就是可以任意的，然后就形成了个区域，对吧？与这个 x 的取值有多少个有关系？
没有直接关系。
比方说2元就可以了。
2元都可以，2元都可以。
我实际上我用2元。
但是我们定义这个区的时候没有限制这个xi 可以取的值，它可以取那个 countably infinite。
如果我把 x 限制到2元，和我把 x 允许它是3元的这个区域，
它是2元的区比较小了，会。
2元的区域相对比较小。
对。
但是实际上你的伽马 n 的定义里面
没有限制。
你只有下马你
没有限制，它是2元3元，它多少元都可以。
只要能计算商就可以。
对，没错。
所有的这些是吧？
对。
这是第一个问题。然后你那个区域的时候，有个 G 乘 H 要大于等于0。
B transpose H 吧。
G 是。
对。G 这个。这个 G， 就是你把那个所有这个 elementary inequality， 它左边都变成 entropy。
对，我知道，我就想知道这个 G 这个 G 会不会是2元
？2元。
就0，给我感觉你要不是正1负1 0，给我感觉。
我看看那个 G， 有可能吧，我要想想。
我在想这个问题，然后同时呢，我觉得呢，至少呢，它可能是整数里面的东西。
对，它肯定是整数。
不会出来分数别的，因为这个所
没错。
不等式的载法。
没错。
这是我这个问题啊。如果我觉得很。另外呢，关于群这个联系我们要求一个群交换群。
不需要。
不需要交换群。
什么群都可以。
好，那但是有限群
有限群。
但是我能不能说在群的元素上，我认为有一个随机变量是均匀分布在群的元素上的，是均匀分布的。然后呢，我是不是可以，这俩是不是就相通的？
它就是那个它证明是那个，其实那个跟你说的这个是类似的，就是我用一个群来 define 一个 random variable。
因为你后面的 log 实际上是一个群的接的大小去 log。那实际上就是均匀商的最大值。是均匀商。
对，它那个你是会用一个群来定义一个 random variable， 也可以用一个 random variable asymptotically 那个定义一些群。
好，就这么的，谢谢你。
So, any more questions?
Why proving the non-trivial type inequalities remain so challenging?
没有工具。There's no tool. I mean, discovering one is not trivial. I mean, trying to see. I mean, to propose some is already non-trivial, and proving one is also is again non-trivial. Okay, actually, you know what, the work by Matouche actually is quite fascinating. He was able to okay. He was able to show that the closure of gamma 4 star actually is not a polytope. There's a curvature on it. Yeah, it's pretty weird. That's why it cannot be characterized by finite number of linear inequalities.
So, any more questions? If there are no more questions, then let's thank Professor Yeung again.
Okay.